In this video, we are going to study how to compute the particular paths in graphs, which are the shortest paths, the shortest that will connect two nodes. This is known as the shortest path problems. It can be solved by several algorithms such as Dijkstra, Bellman-4, or Flood-Warsaw. And what we are going to see is not just the algorithms or how the solution is computed, but in order how to explain what is the notion of the shortest paths. So first of all, as in previous videos, we are going to introduce some notations. We are going to consider a weighted graph G with the three elements, the set of nodes, the set of edges, and the function of weights. And this function assigns to each edge or arc a weight that will be usually a natural number. Whatever we are going to see in this section will be applied for either directed or undirected graphs. So in the case that there is no explicitly weight assigned to some edge or arc, what we are going to see can be applied if we consider that in these cases the weights are 1. So the shortest paths problem stands that if we have a weighted graph G with a weight function W and a given pair of nodes U and B, what is the shortest path between U and B using edges that we have in the graph? And we will understand also that the weight of a path is the sum of the weights of the edges and arcs that form it. So given a weight function and this pair of nodes, U and B, that we are going to compute the shortest path between them, we are going to take some considerations in order to set what is the shortest path. So if the graph is directed the shortest path from U to B and from B to U, they may be different because maybe we can find that there are some edges or arcs that can be used in one direction but not in the reverse. So also the shortest path between two nodes needn't to be unique. It can be reached by different edges or sequence of edges in a path. Besides, the distance between nodes of different related components is considered to be infinite since both nodes can be not reached one from the other. Also, the distance from a node to itself will be always considered to be 0. And the shortest path can be given by an edge or an arc or by a sequence of some of them. So let's go to see some examples about computing what are the shortest path between two nodes, in this case A and B and A, in different graphs. So in the first graph, the one in the left, what we have is that the shortest path from A to B is AB, because the other option that we have is ACB, and it will be of length 2, and in the first case, using just one edge, what we will have is that the length is 1. For the second graph, the graph in the middle, what we have is that the shortest path in this case is ACB of length 2, because we cannot use, there is no arc AB, the arc is BA, and we cannot use it because it's in the contrary sense. And finally, in the third case, we have changed the direction of this edge, and now we have that in fact the direction, the shortest path from A to B is just 1 using that arc, right? In contrast, if we consider the shortest path from B to A, in the first case is also 1, the same as in the second, but in the third one, there is no shortest path. The distance will be infinity because we cannot reach from B to A. Now let's go to see, in the previous example we have that the graphs have weight 1, but in this case what we have is that the graphs will have different weights. So what we see that, let's go to compute again the shortest path between A and B and A. So if we're with the graph on the left, what we have is that we have to take into account that the weights are the number that we have assigned, and don't to be mistaken by the length in the picture that we draw in the graph. Of course, there cannot be a triangle with lengths 1 and 3 and the other side with length 5, but in fact, if we are making a representation, this can make sense as it is drawn. So in this case, the shortest path from A to B, it will be through C, because 1 plus 3 is 4, which is smaller than 5. And this is a case with even a path can be with shorter distance than just one edge, as we have here. For the second case, again, we have that the shortest path is 4 through ACB, because we cannot use even. We don't have even the doubt, because we cannot use connection from A to B, because the connection here is BA, right? And in the third one, we can use that connection, but still the shortest path is ACB in all the cases with length 4. And if we are considering the case from B to A, the first case we have BCA with length 4 as before, right? BA, because we just have one edge connecting them, so that was the solution, it's length 5. And in the third case, the distance will be infinity, because we cannot connect B with A. Now, what we can consider is, let's go to see with different nodes. So here we are computing the shortest distance between A and D. So they are in different connected components, strongly connected components in the first one and strongly connected components in the second one. They cannot reach one from the other in none of the sense. So there is no shortest path, and we will say that the distance between both of them is infinity. Later, if we are computing, even in the case that we have the weighted graphs, we are in the similar situation, and also the distance between all of them is infinity. And just what we have mentioned in the beginning, there are several algorithms such as Dijkstra, Floyd-Warshall, and Bellman-Ford, and there are some difference between some of them. With Dijkstra, we can apply only if we have positive weights in all the edges, right? In the case of Floyd-Warshall and Bellman-Ford, we can even apply if there's some negative weight at some edge, but we cannot have a cycle with total negative weight. So what is this? So what we see in the picture is that we have a graph, three edges, one negative edge, but if we look at the cycle is 5 plus 3, 8 minus 1 is 7, so it's still of positive total weight. So we could apply one of these algorithms to find the shortest path. Nevertheless, in all the cases that we are going to see in the course, our graphs will have positive weights. And so therefore there will be no problem. In any case, we are not going just to get deeper into these algorithms, but we are going to use the results that provide the computation of the shortest path in our graphs. And that's all. Thanks.